Thanks, Miroslav.
Thank you, Mina, for the introduction, and thank you everyone for coming. I'm going to tell you about my work in progress with Davide Gaiotto that is hopefully going to appear soon, about some new interpretation of well-studied objects and important objects in the theory of vertex operator algebra, such as Miura operators and degenerate fields, and their interpretation as gauge-invariant intersections of M2 branes and M5 branes. So let me start very slowly with reviewing some basics of probably the simplest vertex operator algebra, which is the GL1 current algebra. For the purpose of most of the talk, this simplest VOA is actually going to be sufficient for making most of the claims. So the GL1 current algebra, or the Heisenberg VOA, is generated by a single field JZ with an operator product expansion given by the following formula that captures the singular behavior of the insertion of the two operators JZ, or the fields JZ and JW, and bringing them together. Each vertex operator algebra leads to an associative algebra of its modes, with commutation relations recovered from the operator product expansion by a simple contour integral deformation argument. So in our case, we can take the following expansion of our field J, identify the different modes Jn, and recover the commutation relations by the following contour integral. And you can see that the reason why people call it the Heisenberg VOA, because it's composed of infinite series of Heisenberg algebras. So the important objects in the theory of vertex operator algebras are highest weight modules for the GL1 current algebra. That is a highest weight module induced from the highest weight state U that is annihilated by all the positive modes of J, and on which J0 acts by the following complex function. And the tower of states in this module is then generated by the action of negative modes on the highest weight state. We can now define the vertex operator, which is the following expression. I will write most of the times only exponential of a of phi, where you should think of phi as being related to j by derivative, as written on the slide. Or you can explicitly write the expression for the exponential vertex operator as shown in the figure in the formula. In the formula, I introduce an operator TA that commutes with all the j's and shifts the highest weight of the highest weight module. And I also introduce the normal ordering that orders all the modes Jn in increasing values of n. The vertex operator is an elementary object in the theory of vertex operator algebras and satisfy various properties. And here, let me list just two of them by giving OPE with the current J and two vertex operators by themselves among each other. Okay. So in the introduction, I'm planning to actually provide you or give you two trivialist sounding observations that will actually turn out to be very deep once we implement the M-theory picture. So the objects of exponential vertex operators acting on the inserted at point Z, acting on the vacuum with those two different signs, can be thought of as formal power series in Z with coefficients in the module induced from the highest weight state epsilon2, with the highest weight epsilon2. Generate a right module for the algebra, for the GL1 current algebra, since we can act by the
Miroslav,
modes.
why is epsilon2 the highest weight? Can you
there will be a reason for that. Here, it might sound as an arbitrary, and you could consider arbitrary A to obtain marginal vertex operators. But these particular vertex operators are going to have a very important property that they are going to be gauge invariant. I'm going to explain what that means later on. For now, let me just specify the exponent as follows. I think you can already recognize that these are some significant objects, but later on, this exponent is going to be fixed by the condition that I call gauge invariance. Okay, so these objects are generate a module for JN modes. And they
also you have the equivalent volume of R4 is a central charge, like is the coefficient in the OP, right? 1 over epsilon 1, epsilon 2. So that's also not accidental, I guess, right?
Can you say it again?
You have a 1 over epsilon 1, epsilon 2, right, as the coefficient in the OPE,
yes,
which is the equivalent volume of R4, right? Yeah,
that's right.
Okay.
Definitely, that's also not an accident, and we'll see all this picture naturally emerging. Yeah, I should have commented on that. You're right. Throughout the introduction, I randomly introduce some parameters epsilon 1, epsilon 2, and epsilon 3. Their physical origin is going to become clear later on. For now on, let's just look at them at some complex parameters and that randomly appear in our in the formulas that I'm going to write, and hopefully everything is going to become clear, or their appearance is going to become clear later on. For now, let me just mention that these vertex operators acting on vacuum are not only modules for GL1 current algebra, but they are also left and right modules for an algebra generated by polynomials in Z and derivatives. Recall that differential operators act on functions from the right by the following formula. Note also that one can get other generators. So here on these slides, I've introduced these T0n and T20 that might also look very random, but later on there are going to be some natural generators of a bigger algebra. And the algebra is going to contain more generators, TMN, that are roughly Zm to the Z to the power m, del to the power of n. And these can be obtained by commuting the elementary T0n with T20. But for now, the only message of this slide is really that there are these natural vertex operators, and they can be thought of as modules for the algebra differential operators and modules for Jn. Let me introduce yet another elementary objects in the theory of vertex operator algebras, which is the Miura operator. There are again some randomly appearing epsilons. There's going to be a reason for them. But for now, let me just introduce this Miura operator. That can be thought of as a differential operator in one variable with coefficients in GL1 current algebra. And this Miura operator is a very important object in the theory of BOAs because it is known to produce other vertex operator algebras realized in terms of an embedding inside the tensor product of GL1 current algebras, as I will review later. And letting this Miura operator act on the highest weight state with the highest weight 0, we obtain a differential operator with coefficients in the module induced from the highest weight. And this generates a module for both Jn, but also bimodule for our algebra from the previous slide generated by T0n and T20. Since we can now act from both right and left and obtain another differential operator with coefficients in our module of the highest BOA. So right now, what I've done so far, I've told you there's a vertex operator algebra.
What is the left? What is the left action? I guess what is the right action?
What is the right? Okay, so the right action is that you can just compose. I could have added some examples, but So imagine how look at an example of say T01 acting from the right. So what I would do, I would take the element written on the top of the slide and write Z on the right of the expression. You can now commute the Z to the right and obtain a differential operator in a standard form with the derivative being on the right and functions of z being on the left. I can try to.
You mean you can compute it to the left? You can insert it on the right and move it. I see. Okay.
Exactly. That's right.
Okay. All right. No, just keep going.
Yeah. Nothing fancy. Yeah. Nothing fancy. Really, I'm multiplying either from the right or from the left.
Yeah. No, that's fine. That's fine.
We'll see some examples later on as well. Okay, to a short recap, I've reviewed some basic elements of the vertex operator of the Heisenberg VOA, and I told you that Miura operators and vertex operators are naturally modules for both the vertex operator algebra, but also for the algebra of differential operators. Now, the trivially sounding observations turn out to lead to very deep statements. If you realize that M2 brane living on R times C epsilon free, where by the subscript epsilon free, I mean that I turn on equivariance for the C star action that rotates the C, or in physical terms, turning on omega deformation with parameter epsilon free. And this M2 brane leads to topological quantum mechanics with the algebra of Coulomb branch operator with quantum mechanics living on R, with the algebra of Coulomb branch operators generated by z to the n and a derivative, which is exactly the algebra that appeared in the observations from the previous slides.
And z here means what?
We are again going to give an interpretation of this z.
Okay. Yeah.
Yeah.
Z is the position on this complex plane with no epsilons, right? Is that
exactly? That's right.
Okay.
Yes.
Good.
I'm going to give this picture later on, but basically how you should think about the z. Z is the position along one of the c's in the orthogonal directions in M theory, and the derivative is a position along the other one. So there are two extra c's. We will see that later. Okay, now M5 branes wrapping C times C epsilon 1 times C epsilon 2 analogously leads to holomorphic quantum field theory on C, the undeformed C, with an algebra of introduced previously with the Miura operator, generate modules for both of the algebras. And the purpose of this talk is to convince you that these operators actually can be interpreted as building blocks of gauge-invariant operators describing M2-M5 brane intersection. I will have to describe what I mean by gauge invariance, but this is going to be the main message of this talk. And this also turns out to lead to deep connections between W algebras associated to M5 branes and Coulomb branch algebras associated to M2 branes, with consequences such as categorification of the relation between Johnson-Thomas and Pandari-Pandey topological vertices and more. I'll briefly mention those applications, but unfortunately I won't have much time to discuss them in great detail. So now the promised physical setup, where we start like kind of recovering the appearance of the epsilons that I introduced in the introduction, and we'll hopefully gain some understanding what is the physical setup I'm interested in. So let me look at M theory on flat space in the presence of omega background turn on along three of the C's. So this is going to be our geometry, where we turn on omega background along three of the complex directions with parameters epsilon I that sum to 0, which is just a condition that the volume form, the holomorphic volume form on C3 is preserved by the corresponding C star action. We can now place various M5 branes and M2 branes inside the setup. inside this this configuration, inside the geometry. And in particular, I decide to put N1 branes, M5 branes along the first C.
Miroslav, I at least have an echo.
Similarly, N2-M5 branes and N3-M5 branes. So can you say it again?
At least for me, there was some echo where I lost a couple of sentences. I'm not sure if the case was for others. If others were okay, we can just go.
Yeah, I think there's delay on my end too.
Okay, I can start with.
So I don't think you have to go on for the beginning. Just repeat maybe the last two sentences.
Again, maybe.
Yeah, and hopefully it's not going to happen.
Okay, so the only thing I said. Yeah, so I only said that we have this M theory in this flat space with those M parameters, and I described that I'm going to put M5 branes along one of the C's and wrapping two of the omega deformed C's. And there are 3 different ways how we choose which C's in the omega deformed part they wrap. And I'll put N1 M5 brane along one of them, N2 M5 brane along the other one, and N3 M5 brane along the third one. I can do the similar thing with M2 branes by wrapping N1 M5 brane along R times C epsilon 1, and analogously for N2 M2 branes and N3 N2 branes wrap the other deformed C. So from the perspective of the directions C times R, the first 3 directions, the M2 branes lead to a surface operator labeled by 3 different parameters, N1, N2, and N3, measuring the number of M5 branes with the given orientation and living on C inside this C2 times R. And analogously, M2 branes lead to a line operator, again parameterized by 3 different numbers, living on R. Okay, let me now add a slide with some references. So the word volume theory of N3 M5 branes in omega background lead to vertex operator algebras that I denote for the purpose of this talk Y00N, usually denoted as WN algebras in the literature, living on C. This is due to a version of AGT correspondence. There exists a 3-parameter generalization of the story, and if we introduce those different M5 branes along the different 4 cycles inside this deformed Calabi-Yau threefold, which is just C3 in our case, we can the configuration of M5 branes leads to a more general surface operator that I denote as S, N1, N2, and N3, with a corresponding algebra Y, N1, N2, N3 from our previous work with Davide. On the other hand, the 3-dimensional supersymmetric gauge theory in omega background is known to lead to Coulomb branch algebras of local operators living on R. This is a story that received quite a decent interest in the past couple of years. And the theory associated to N3 M2 branes living on C epsilon 3 times R has a UV completion in terms of an ADHM quiver gauge theory, with the Coulomb branch algebra studied by Kodera and Nakajima and interpreted in our context by Costello, leading to Coulomb branch algebras that I denote as A00N3. One of the results of today's discussion is going to be a 3-parameter generalization of these algebras, A, N1, N2, N3, associated with the general configuration of M2 branes, leading to the line L, N1, N2, and N3 in M theory picture above. Okay, so far from the M theory perspective, we learned that there should exist a generalization of the Coulomb branch algebra studied by Kodera and Nakajima. Let me now harvest M theory a bit more and recall some results of Costello's recent work on twisted M theory. So according to his proposal from 2017, twisted M theory in our background should have a description in terms of a GL1 5-dimensional non-commutative Chern-Simons theory with the action given by the following formula. And the theory living on RC2 times R. So in this action, I've introduced the star epsilon, which is just a non-commutative generalization of the standard wedge product.
There's one more integral, right? There's some integral over line.
Well, so by the integral, I mean an integral over the whole space-time. The dz1, dz2 is just the holomorphic volume form on C3, C2. And the A, dA, and similarly, don't forget that A is one form, and epsilon and the star is just wedge product, basically just a wedge product. So the Chern-Simons function ADA plus AAA produce a free form that can be wedged the canonical holomorphic form.
I'm saying if it's a 5D theory, there should be one more integral, right? So integrate over which, yeah, so integrate over 5-dimensional space. So there's one R and then there's a wedge. What is the topology of the space-time?
The integral is over R times C2.
Okay, okay.
Yes, so I'm just integrating 5 form over C2 times R. But the details of the theory are not going to be very important for the purpose of this talk. I just want to use it for a motivation of the statements that I'm going to make, algebraic statements. The reason why I write this action is because to argue that the 5-dimensional Chern-Simons theory before deformation has a large gauge symmetry, because I can shift A by d phi for phi being an arbitrary function, holomorphic function on C, because this term when wedged with dz1, dz2 just trivially vanishes. And the non-commutative deformation just leads to an obvious deformation of the algebra of gauge transformation that is generated by by Z1 and Z2, satisfying the following commutation relations. And the consistency of the theory with the presence of R surface defects S and L just require that operators on this surface defect S and line defect L must admit a consistent coupling to this 5-dimensional Chern-Simons theory.
Miroslav, can you remind us just to refresh our memory, how did Costello's argument go to derive the 5D Chern-Simons?
I think it is pretty indirect. He uses some sequence of dualities to end up with a setup with a brane description. So I think the way he does it, he actually exchanges the C2 by top knot and does a duality along the circle of the top knot to obtain a description of the same system in terms of on D6 brane on yeah, in omega background. And then by compactifying on the omega background of this D6 word volume theory, he receives a 5-dimensional action, and he proposes that this 5-dimensional theory should be the one describing the corresponding geometry.
And what drove the symmetry between the epsilons for him?
The way how he compactifies, he first compactifies on one of them and then compactifies on the other one.
Or maybe he reduced on some combination of actually on the C's with epsilons on them. I think that was where the problem was. That would break the symmetry, I think. Yeah,
that sounds right. Yeah,
and then
I would have to.
Okay, good. Yeah, I think that's right. Okay.
Yeah, I would have to recall the details. Mm-hmm.
I just needed to sort of place it somewhere. Great.
Yeah, good. Okay, so classically, one expects that the line L, N1, N2, N3 coming from M5 branes can couple to to the gauge connection A and possibly all its normal modes by some generators T-M-N satisfying relations of the gauge algebra. So as argued by Costello, this expectation actually receives quantum corrections, and the vanishing of the gauge anomalies actually require the generators T-M-N to satisfy relations of an algebra A deforming the classical gauge algebra. The algebra A is an associative algebra generated by elements T20 and T0n with other generators defined in terms of the following formula, and all the relations that can be determined by using the seed relation commuting T30 and T0d. This relation in particular introduces an explicit dependence on our parameters, equivalent parameters epsilons, epsilon1, epsilon2, and epsilon3 that sum to 0. And this dependence is triality invariant, manifestly triality invariant, where the triality just permutes the epsilons, since the formulas depend only on the triality invariant combinations, epsilon, sigma 3 and sigma 2. Note also that A admits truncation map to the Coulomb branch algebra A001 associated to a single M2 brane along the third direction. This truncation map is given by the following formulas. And these are exactly the formulas that I wrote in the introduction. So they were not really random, but they come from this natural truncation map. And one can check that these indeed satisfy the relations from the previous slide. Analogously, permuting parameters epsilon1, epsilon2, and epsilon3 gives rise to 3 elementary truncation maps from the algebra A to L100, truncation maps L100, L010, and L001.
Can you explain a little bit more what you mean by this truncation? What are we doing?
Maybe, okay. Right. Let me use an analog of the M5 brane story that I'm actually going to review next. But let me first say it here. So in the case of M5 branes, all the algebra governing or describing the M5 brane algebras, vertex operator algebras, is W infinity. The different algebras associated with given choice of M5 branes and their orientations correspond to the truncations of the W infinity algebra to Wn algebras or their generalizations. This basically corresponds to.
Just a second. So tell me again, what is W infinity algebra for you? What does it do for you?
So I haven't introduced W infinity algebra yet. W infinity algebra is going to be relevant for discussion of M2 brane.
I see. So you're saying that M5 brane algebra is a truncation of the double infinity algebra, and this.
That's right.
The Wn algebras, good. And so the analogy was supposed to be just so I can connect it in my head. The analogy with M2 branes is then what?
That algebra A plays the role of W infinity.
Oh, I see.
And algebra A, M, and N plays the role of Y, M, and N. The corner VOAs. So the
truncations of this algebra A are the M2 brane algebras. Is that? That's correct.
That's right.
Absolutely. Okay. And what is the relation between the algebra A and the M5 brane algebras, or the double infinity?
So this is the relation that we are going to talk about when discussing all this.
Okay. Great. Okay.
Gauge-invariant. But let me say it very briefly here, and a statement that I'm actually not going to make again later on because it requires slightly different perspective. The M5 brane algebra has an alternative description in terms of a fine Youngian of GL1. The M2 brane algebra is a subalgebra of this algebra that goes under name one-shifted affine Youngian. Yeah.
It's a subalgebra or a particular representation of that algebra? It's strictly a subalgebra?
I mean, the different truncations to M2 brane algebras are going to get a different. So you should think about A as a unifying algebra, and then different truncations coming from the truncation maps, giving rise to the M2 brane algebras.
Okay. Great. Okay, excellent.
Okay, so let me now turn to the M5 brane story. So an analogous argument from Kostel's work from 2017 leads to conditional local operators on surface defects S and N1, N2, N3 descending from M5 branes. They should admit a consistent coupling to the 5-dimensional Chern-Simons theory. In particular, vanishing of the gauge anomalies in this case requires the surface defect S, N1, N2, N3 to couple to derivatives, again, normal derivatives of A to the in the normal direction to our surface operator. Some operators Wn that now depend on the position Z on the surface defect, and that they have to satisfy relations of W infinity algebra generated by W infinity algebra. W infinity algebra is an algebra generated by infinitely many fields, W1, W2, W3, and so on up to infinity, with the subscript labels conformal dimension of the field. And it is an algebra studied by many, many people. I wrote just a few of them. And they satisfy a system of operator product expansions that is quite hard to write down explicitly, but I write down at least some OPs of the first few generators. And I decided to write it in manifestly triality invariant way, since you can see that the OPs again depend only on the triality invariant combination sigma 3 and sigma 2, and an extra parameter psi 0, which is a central parameter. Analogously to the M2 brane algebra, this W infinity algebra admits truncation maps. And in particular, note that the GL1 current algebra associated to the simplest surface defect S001 satisfy relations of W infinity, and one can write down an explicit truncation map given by the following formulas. And I pick a particular normalization of J's, being 1 over epsilon 1 over epsilon 2, where epsilon 1 and epsilon 2, where the prefactor is exactly, as mentioned by Peter, the equivalent volume of the for the given C2 inside C3. Similarly, there exist elementary truncation maps S100 and S010 obtained by permutation of parameters epsilon 1 and leading to other elementary algebras Y011, Y100 and Y010. So these truncations are going to be sufficient for most of the discussion. But let me just mention at this point, just to give a complete picture.
Are we supposed to think about this truncation as somehow saying that it's double infinity acting on M2 branes, that basically everything, all the higher W's kill it? Is that a statement? What are we doing? I'm somehow losing the space-time picture as to what's happening. Or just some picture of what's happening other than the algebraic one.
So I'm just saying that the algebras, that there's a general argument coming from this five-dimensional Chern-Simons theory picture that require the line and surface operators to couple to the 5-dimensional theory by operators that satisfy these algebras W and A. This is a calculation that Kevin did by looking at perturbation theory in this 5-dimensional setup. In particular, that means that the algebras that all the algebras L, N1, N2, N3 associated to M2 branes and algebras S, N1, N2, N3 associated to the M5 branes must satisfy the relations of W infinity and must be representations of the different representations of the algebra W infinity or the algebra A. And the truncation maps are just the representations.
Okay, thanks. That makes sense.
And I call it truncation because these algebras satisfy some, so these are not, these representations satisfy some extra relations. They're not faithful representations. Okay, and in general, something that we are going to see later on, there do exist truncation maps from W infinity and from algebra A to more general algebras living on the surface defect S, N1, N2, N3, and the most general algebra of operators living on the line defect A, N1, N2, and N3. But also the elementary truncations that I described quite explicitly in the previous slides are going to be sufficient for more talk. Okay, there was another observation pointed out by Gayotta and Oh in last year, that there should be there should exist a L tilde N1 and ending from two different sides on S, N1, N2, and N3, and corresponding to the following configuration. So you should think about yeah. One can expect that the gauge invariance condition receives contributions from all the operators involved, and somehow deforms the naive constraint of the following form. And the main objective of our work was to identify the precise condition for this gauge invariance and explore its mathematical implications. So let me now state the gauge invariance condition. It is straightforward to check that the following formulas that I write give a coproduct from A to A times W infinity. You can also see that these formulas somehow deform the gauge invariance, the naive gauge invariance condition from the previous slides, since they map the tilde generators to T to the sum of a generator of A and a generator of W infinity algebra. I've introduced V-2, which is a mode of some which is just a minus 2 mode of some W infinity primary, given explicitly by the following expression. And it is a straightforward check, 3 pages long, that this map actually gives rise to a well-defined coproduct from A to A times W infinity. And we have now all the ingredients to state the gauge invariance condition, deforming the naive condition of the following form. So we suppose that the gauge invariant operator describing intersection of our Ln1, N2, N3 line with L tilde N1, N2, N3 with the surface operator S N1, N2, N3 is given by the following expression. And this is I think the main result of our paper. Let me decodify the formula a little bit, just to make sure that that we understand what it says. So first, let me start with the generator TMN on both sides of the expression. On the left-hand side, we map TMN to the algebra A, N1, N2, and N3 by the truncation map L. On the right-hand side, we first map it by the coproduct formula from the previous slide that sends a generator of A to A times W infinity, and compose the result with the truncation map for the line defect and a truncation map for the surface defect. We then act by the first one from the right on the vertex on the on the operator O, describing the gauge-invariant intersection, and we act by the other one, the composition of the two other maps on the right of the operator O. And the claim is that the gauge invariance condition says that these two are equal. I'm going to illustrate this gauge invariance condition on these very simple, on these simplest example, the elementary building blocks that I introduced in the introduction. And in particular, it's going to turn out that many key objects in the theory of BOAs can be now given an alternative interpretation in terms of gauge invariant junctions of in terms of describing gauge invariant operators describing junction of M2 and M5 branes. So let me now look at the...
Is there a way to say state your relation somehow, let's see, geometrically in terms of...
well, I would love to.
Okay, let's see. So, okay.
Well, if you have any idea, I would be more than happy to hear it.
I mean, the M2 branes are, I mean, they are like, they're point observables in the M5 brane theory, right? And junctions of the M2 branes are, I mean, you're just inserting on this Riemann surface, right, where your CFT lives, and all these M2 branes are just points.
Yes.
So so from perspective of right, can't one somehow say this?
Yeah, so the Z should definitely, so Z should be thought of as describing position of the M2 brane along the C where the vertex operator live. That's right.
Yeah. Is the issue that your theory is not truly two-dimensional? Is that it's not really an honestly two-dimensional CFT, but somehow that is really four-dimensional? Is that somehow why you can't say it in some straightforward way as some word identity in two dimensions? I mean, or result of some word identities in two dimensions.
Yeah, I think so. I think so, because I'm trying to like rephrase it from the perspective of, I would say the 5-dimensional theory, or at least like it's a 3-dimensional slice or something like that.
You mean?
So I'm really looking at. Yeah, I'm really trying to look at those objects from not only from the perspective of the BOA, but really by combining the like all the directions.
And can you say, okay, maybe the way of asking it is, maybe I should let you go on actually with your talk. So let me not interrupt. Let's keep going, and then I can try to maybe talk at the end.
Okay, sure. Okay, so let me illustrate the gauge invariance conditions on these 3 elementary junctions. From the M theory perspective, it's also obvious that these 3 elementary junctions are going to be the basic building blocks out of which we can compose an arbitrary other gauge invariant intersection. So let me start with the example of the following vertex operator. And let me test it's that I associated to the following simple configuration of the line L100 ending on S001 from the right. And let me test its gauge invariance. So on the right-hand side, composing the coproduct from A to A times W infinity with the trivial truncation map that sends all the T's to 0 because there's no line on the left. This produces just an embedding to W infinity. So from this perspective, you can already see that there has to be an embedding of A inside W infinity, and there indeed is. And the gauge invariance condition simplifies to the following statement: that the operator O should intertwine the right action of A100 and the action of A100 via its image in Y001. Let me write down some formulas, what I mean by that. So when writing in terms of formulas for these generators T0n and T20, we'll get the following conditions. And you can indeed see that this vertex operator somehow non-trivially intertwines the right action of the Coulomb branch algebra, the algebra of differential operators in single variable, in this case, and the action of the modes of the W infinity, or in this case, just Heisenberg VOA. And I write down the relevant truncation.
The right, so there's sort of two orderings, right? One is the operator ordering on your Riemann surface, where the CFT is supposed to live, or the intersection of M5 rings. And then you have a second ordering, which is in the Strasser's direction. And somehow we're mixing them up here.
Yes. Are we?
Are we?
I don't think so.
I mean, when we talked, when you, so for example, in here, you're saying that M2 ends on the left versus on the right. Is because it was ending on the right, is this why you wrote this in such an order? Maybe I'm not following.
Not necessarily, because there will be some sign issues with the action of the derivatives. So you do have to be, but that's right. You can look at the formulas as really following from the picture. So here we had some gauge on the previous slide. We had some gauge invariant combinations that I said that it's supposed to be the O acting on the vacuum, and we should have a right action of the generators of the L algebra, of the line operator algebra. So this is exactly what I write on the left of the formula. And the gauge invariance condition is just a statement that the anomaly in flow governed by the action of the L tilde generators should be cancelled by the inflow from the surface defect, which is governed by the action of the modes of the W algebra from the left. So I do always act by the generators of the W algebra from the left, but according to the picture, I act by the Coulomb branch algebras either from the left or from the right. Okay, let me now look at another example of the vertex operator with the opposite sign that I associate to the endpoint of line operator L100, ending on the surface defect from the opposite side. So in this case, the generators T, and there should be tilde now. Sorry. So in this case, the generators T, M, N now act trivially from the right, but the action on the left becomes more complicated, leading to another conditions. So we plug into the general condition that I wrote before, all the truncation maps that I write explicitly on this slide. We get the following condition, and again, one can sit down and check that the vertex operator satisfies it. Similarly, the Miura operator, given by the following function, is another elementary junction that I want to introduce. I want to associate to the following intersection. know that piercing the surface 0, 0, 1 with a line of different orientation, say L100, is not an elementary junction because it could be composed from the previous two examples. Because in the full M theory setup, the corresponding M2 brane can actually end on the M5 brane, compared to this situation describing an intersection of L001 with S001, and thus this is indeed an elementary junction. So one can combine the two gauge invariance conditions from the previous, from the two truncation maps from the previous two examples, and check that this Miura operator, when acting on the vacuum, indeed satisfies the gauge invariance condition again.
So this was an M2 brane that can't end, a single M2 brane that can't break on the M5 brane. It's somehow oriented in such a way. Okay.
That's right. I'm going to recover later on, or at least sketch how to recover the general Miura operator associated to other orientations of M2 branes later on, but I'm going to recover them as expected from the two endpoints. But before that, let me look at the fusion of the gauge invariant junctions along topological direction. So the elementary junctions, as I promised, can be fused in various ways. They can be fused in holomorphic direction, leading to related to a holomorphic coproduct on A, or they can be fused along the topological direction, leading to a topological coproduct of W infinity. So the Miura operators serve in the literature as an object producing algebras Y00N by so-called Miura transformation. Let me first look at the simplest example when N3 equals 2. Taking a product of two Miura operators, as I write down here, and expressing it as a differential operator of a second order in standard form by commuting all the derivatives to the right. We can identify the coefficients in front of each of the derivative. And it is a well-known fact that the corresponding fields, in this case U1 and U2, generate an algebra Y002, which is just the Virasoro algebra tensored with an extra GL1 current. And the Miura transformation above gives rise to a coproduct from Y002 to Y001 times Y001. So this is a standard construction in the theory of VOAs. But from our previous perspective, one can naturally expect that composition of these Miura operators describes a junction between the surface S002 coming from the fusion of two trivial surfaces with line L001, as in the figure. And analogously to the simple example of single Miura operator, one can again sit down and check that O acting on the vacuum indeed satisfies the gauge invariance condition, with Y002 generators now acting via the embedding or the coproduct that sends Y002 into Y001 times Y001, the elementary Heisenberg VOAs.
And does what keeps track of? I see. So nothing knows about the distance in the topological direction, right? Because it's topological.
Yes, exactly.
But you know it's non-zero.
But the whole,
I guess you don't even know it's non-zero. I guess you do know probably it's non-zero. Okay. 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 Yeah. As long as probably as long as it's non-zero, you get this. And if it's zero, then you don't know. Okay. Okay. Mm-hmm.
That's right.
Is there any, if we were to reorder them, can you pass them? What happens if you reorder them? Do you get the same thing?
You don't, and that is actually a story that that we haven't investigated, and I don't know. So the embedding of the universal algebra inside the tensor product does depend on the order of the Miura operators. This gives rise to two different embeddings. These two are related by charge conjugation of the W algebra that somehow corresponds to the reflection along the plane parallel to the surface operators. But generally, if you have more of the surface operators, you are going to get different embeddings depending on the order of the surface operators. These should be somehow related to the Maulik-Okounkov R matrix and the story about R matrix, but I haven't investigated it, and I don't really know. I don't really know how exactly it depends on the ordering.
Okay, but I mean, so a single Miura operator for you is an M5 brane and an M2 brane piercing it. That's what it corresponds to.
Yes, exactly.
Okay.
Exactly. Yes. Yeah, that was basically like this observation was basically the whole motivation for the project. At that time, we had no idea what the gauge invariance means and what exactly this statement means. Now we feel that we have much better understanding because we do know in what sense, like how to kind of at least kind of make sense of this statement.
Which,
yes.
Okay. Okay.
And Z is the coordinate of the intersection, or where the brane goes.
Exactly. So Z is a position of the line operator L in the plane of the surface defect.
And suppose I take two of these guys where Z's don't coincide.
Mm-hmm.
How is this consistent with this picture?
It is absolutely consistent because this is actually going to lead to, again, gauge-invariant intersection that is going to intertwine an action of algebra A200 that I'm going to define later on. I'm not going to talk about this particular example, but again, you're going to, by composing the same Miura operators at different positions, is going to lead an operator that intertwines between Carl-Jérôme-Moser integrable system that governs the A200 algebra with the Heisenberg VOA. So the composition. So you're proposing the following calculation. Take a single surface say S001, and pierce it by two different lines at two different locations.
No,
right?
no. What I want you to do is I want you to take your picture, but make a mistake. Instead of inserting these Miura operators as the same value of Z, I wanted to insert them in different values of Z. So one is Z1, and the other one is Z2. It seems that this would force you to actually have 4 Miura operators, not 2. Two for each plane. Because they would, if it's an M2 brane, M2 brane just doesn't stop.
Yeah,
right?
but
so it just goes through.
How to have one half of it, right? He knows how to just do the one half of the brane, but kind of terminates on the.
It can't end. These branes cannot end. That's why they're Miura operators.
No, they can. They're just not going to be Miura.
No, not these. So there are M5 branes on which M2 branes cannot end. It depends how they're oriented in space-time. On these, they cannot end. Right?
This is very important because they intersect only at the point. This particular configuration. Later on, we'll see how to decompose them into halves. But for the other Miura operators, along C. That's what we're going to see later on. But whatever calculation you are suggesting, Mia, I'm pretty convinced that if you try to probe the gauge invariance, you wouldn't be able to satisfy it.
Okay. And sorry, so which gauge symmetry are we preserving here?
So this will be all about the gauge symmetry of the full coupled setup, full setup of the 5-dimensional Chern-Simons theory in the presence of surface and line operators. So the line operators cannot break the gauge invariance. They must couple in gauge invariant way to the 5-dimensional Chern-Simons theory. And I believe that all the gauge invariance condition, everything that I'm talking about here, should follow from the 5-dimensional Chern-Simons theory picture. This is something that we haven't done. We have just like identified the gauge invariance conditions by some algebraic analysis, and check that various natural objects from the theory of VOAs actually do describe these gauge invariance conditions, and it nicely fits within the M theory setup and all the M theory configurations you can come up with.
So the gauge.
The reason the only reason I call it gauge invariance is really because they should follow from some gauge invariant, that's vanishing of some anomalies in the calculation of 5D Chern-Simons theory.
So gauge field in 5D Chern-Simons theory, it originates from a 3-form in M theory. There's nothing else.
That's right.
Good. So all the anomalies you're talking about have to do with the 3-form in M theory. In other words, there are some kind of anomalies in M2 brane charge conservation. No. Okay. So, okay. My question was motivated in trying to simply understand your dictionary, but just keep going. If we're not making, yeah, let's go.
No, really, you're supposed to think about the Miura operator as the M5 brane, the M2 brane piercing M5 brane, and
except that M2 brane exists for all values of this parameter, this real line. It can't stop. Well, it can only stop, but it can stop at some other M5 brane, at some S100 or S0010. It could stop on them, right?
But I'm not stopping them.
Good. So okay, Ruth.
I'm not stopping them because I can from the left and from the right.
Okay, I'm not thinking about it correctly. I think what I should be, the way I think you want us to think about it is that this operator that you wrote down up there simply actually corresponds to this picture that you wrote down. that is the picture that goes with that. And it's not really obtained by taking a product of two Miura operators because you can't decompose them. I mean, the only way to decompose them is to insert, say, another M5 brane in the middle so that, you know, M2 branes can break and you can bring them from infinity or something like that. That's the only way it can become a product of two things as opposed to just one thing. Just from string theory, right? Because this
no, but what's the problem with separating those branes?
So this M2 brane cannot break. It's a single M2 brane that, as we wrote it, it cannot break. Yeah. So it's not a product of anything. It's not in any way, in any sense, decomposable, unless you say add more M5 branes. Then it can break on them, and you can build it out of two pieces. But as the picture. Yeah,
that's a good point. But that's something that we see within our setup as well. And I'm not trying to move the middle part. I'm not trying to move the middle part. The only thing how I think about the taking product of the two Miura operators is really by taking the configuration as drawn in the figure there. The whole line goes through everything, doesn't end anywhere. I'm not moving it anywhere. The only thing I do, I compose the two operators O that lie at these two intersections. But I'm not trying to do anything with the M5 brane. I have a single M5 brane, and I just collide the surfaces. And the M2 brane is just a probe of whatever I'm doing with M5 branes.
Okay, so again, I guess maybe the confusion is about what this ordering means. Again, so I guess the ordering of your operators is the ordering left to right along the line.
Yes.
Okay. Okay.
That's right.
All right.
That's right. And everything depends on the ordering, because if I switch the order of the Miura operators, we would get different embedding inside of the Virasoro algebra inside this these two Heisenberg algebras, and also different. Yeah. So right. So just the Virasoro would act differently.
Sorry. One more question. You said that something you think should be connected to something that Okunkov and Maulik did. What is that?
So they developed this whole theory about R matrix for W algebras and these kind of things. And to my understanding, this R matrix relates the two different ways how to do Miura operator. I've never studied. Actually, Tomáš is here, and Tomáš wrote also a paper on the Maulik-Okunkov R matrix, so maybe he can comment, but I'm not sure if he wants to. But anyway.
Well, can I ask a question?
Uh-huh.
Yeah. So do you mean there are metrics going from dominant chamber to anti-dominant chamber, and that it can be decomposed? So there are metrics depends on going from one chamber to another, right? And so either you sit in like the root system A1, and you have the only wall to cross, or like then the only like other natural things I can think of is like going from dominant to anti-dominant chamber. Like what exactly like R metrics you expect here?
Well, honestly, I haven't studied what they're doing, and I don't want to dive into this discussion. I just want to make a comment that there might be relation. To my knowledge, the order of the Miura operator is somehow related to the R matrix of Maulik and Okunkov, and yeah, I really don't want to go into details, but I would be happy to discuss.
Mirek, if you put these two branes, can you hear me?
Yes.
This S001 and S0 tilde 001. If you put them, can you put them on top of each other? Would you say that then you get just Virasoro times GL1, or you would always try to keep them separate? Because there is more degrees of freedom somehow in CFT. If you take two free bosons, it has more degrees of freedom than if you look at U1 times Virasoro, no? Because it's sitting inside.
Yeah. You can do both. You can directly write down the Miura operator for the Virasoro itself, not realizing it's of the product, and it is still going to satisfy the variance condition. And you do not have to study the embedding of Y002 inside the product of two Heisenberg VOAs.
And then in that case, your 5 branes would be like on top of each other in the picture. Or... Yes. Yeah. So then I think this Maulik-Okunkov R matrix just really intertwines between getting this configuration by merging the two 001 5 branes like from in two opposite orders. If you label them, if you go, if you put
so
first
that's
one
like
on left.
So if I have just coordinates like x1 and x2, that chambers like x1 is greater than x2 and the other way, right?
Yeah, in this case, yes. In this case, the R matrix really just flips the sign, so exchanges x greater than y to y greater than x. It's just reflection. This is also what Mirek said.
But if I put like n branes like this, it should be like an.
Yeah, then you can label all these things by Weil group, no? So you can decompose it into product of elementary mergings or exchanges, reflections. One by one along each.
Transpositions, So here is just like really SN and like it's.
Yes, so then if you compose, I don't know how many of them, n factorial of them, or no, maybe less, then you can get from the chamber that you set, let's say when x1 is bigger and x2 is bigger and so on to the opposite one by composing these elementary reflections, and each of them is like implemented by this Maulik-Okunkov R matrix.
Then I understand. Thank you.
Okay, good. Thank you, Tomáš. Okay, so now I told you that composing the elementary Miura operators produces a gauge-invariant junction between this S002 and the single line L001. And analogously composing N3 of those elementary Miura operators should produce gauge-invariant junction between the general S00N3 and L00one, on which the algebra Y00N acts via its embedding inside the tensor product of N3 Heisenberg VOAs. Again, coming from the Miura transformation involving N3 elementary Miura operators with a given ordering of the with a given ordering given by the picture. And to obtain operators associated with general intersection with general integers n1, n2, n3, and n1, n2, n3, we have to work a little bit harder. So let me start with the surface operator associated with M5 brane with orientation 1, 0, 0, and with the line piercing it, line 0, 0, 1 piercing it. So in this case, we can actually split the line into two different parts, since the corresponding M2 brane now can end on the M5 brane, and we can separate them. Separate them. Both of the endpoints then correspond to, according to our previous discussion, to one of the two elementary vertex operators with the two different signs, and describe the corresponding endpoint. And we want to somehow describe how to fuse these two back together to obtain a Miura operator, describing an intersection of S100 with the line L001. So the proposal I'm offering is to take just the product of these two operators, vertex operators, and take a contour integral in the following way. Here, what I only did, I only wrote down the OP of the two exponential vertex operators, and one can rewrite the right-hand side by taking a residue in terms of an overlap of derivative to the power of epsilon1 over epsilon2, conjugated by the vertex operator, the involved vertex operators. What can one do? One can now commute the derivative to the power of epsilon1 over epsilon3 to the right, and obtain a pseudo differential operator of order epsilon1 over epsilon3 with infinite series of fields in front of each of the derivative term. And surprisingly, this reproduces the generalized Miura operator from my previous work with Tomáš, and the fields UI multiplying the different derivatives turn out to satisfy OPs of W infinity and produce truncation map S100 from W infinity to Y100. And an analogous calculation produces operator associated to gauge invariant junction of S010 with L001. So you could really see that those Miura operators we found with Tomáš, and that we were quite surprised about, are nothing but operators that you obtain when fusing the two endpoints, operators associated with two M2 branes ending on M5 brane from the two sides. And composing the elementary Miura operator, describing the gauge invariant junction of L001 with S001, and the generalized Miura operator describing the gauge invariant junction of L001 with S100 and S010, produces a conjecture. This is actually a conjecture because we haven't performed the check completely. It produces a gauge invariant intersection between between the line L001, the general S N1, N2, N3, associated with the following figure. And the standard Miura transformation can be just thought of as probing system of M5 brane algebras by an L001 probe. And this also explains why the description of W infinity in terms of the generator's UI from the Miura operator breaks the explicit reality symmetry. it is because of the of the fixed direction of the probe M2 brane. Okay, so that was an illustration of fusion along the topological direction. Now let me briefly mention.
Sorry, Miroslav, just here you have one boson per M5 brane.
Yes.
One boson.
No.
No.
So what do you mean here? Yes. That's
in your formula
right.
for the Miura operator, the phi is the boson of the corresponding M5 brane.
Yes.
And so what's your proposal? Yeah. And what's your proposal how to get an operator that will correspond to this picture? I didn't understand it. It's just.
So let me come back. So this is the operator that I would associate to the surface S001 coming from the fusion of So this is the gauge-invariant operator that I would associate to the surface to two M2 branes with orientation 3 coming from fusion of two M5 branes along this direction.
I see. So you just keep doing this.
And that's how you can get 00n, arbitrary 00n.
I see.
In order to
every time. Okay.
So every time
an M2 brane ends, it passes an M5 brane, you get a pair of bosons of that M5 brane, and you just keep doing it. Okay.
Yes, that's right. And these other generalized Miura operators just tell you how you can compose more general Miura operators in order to get assemble arbitrary configuration of M5 branes, but always a single M2. Now I'm going to start adding M2 branes. And let me start slowly with a single M5 brane and two M2 branes ending on them at different locations, Z1 and Z2. And it is natural to associate the following vertex operator to this configuration. And let me probe the gauge invariance of the system. But for that, we need to identify what is the algebra A, N1, N2, and N3. So analogously to the coproduct producing Y, N1, N2, N3, there exists a coproduct that can be used to find an explicit realization of A, N1, N2, N3, starting from the elementary truncations A100, A010, and A001. I decided not to talk about this because it would take, the details would take maybe 4 slides. And let me skip the details and just give you the resulting proposal. What exactly is this algebra A, N1, N2, N3? So this is an algebra generated by the following generators. Which are like differential, meromorphic differential operators in N1 plus N2 plus N3 plus N1 plus N2 plus N3 variables. Now the generators T and 0 form a system of mutually commuting differential operators. The fact they are mutually commuting follow from the relations of the algebra A. And they generalize the well-known Cauchy-Moser integrable system. So as a byproduct of our analysis, we get this triple generalization of the Cauchy-Moser integrable system that has not been identified before, to my knowledge.
Well, you need to compare it with the spin culture. So
yes, I think the spin culture
different on a little bit different on the nose, but it might be not so different after all.
Yeah, so to my knowledge, the spin Cauchy-Moser is related to a matrix generalization of the Cauchy-Moser. Then there's also the double Cauchy-Moser that has been identified and is known to act on conform blocks of W algebras and everything. We talked to some people, and it seems that the tripled one has not been written down, and the reason might be the same reason why Wn algebras don't see the third direction of W infinity, but yeah. If you have a suggestion,
for n, right?
what,
So here you wrote it for n equals 2, but you have for t n comma 0, right? They look like n plus 1 different, well, differential operators, like the operas or whatever they are.
can you say it again? I didn't hear
the formula for n equals 2. Do you have, I mean, does it work for any n? So we have sum of n lines, n plus 1 lines this way?
What works for n plus 1?
So the second formula you have t2 comma 0, and you have sum of 3 lines, right? If you replace 2 by n, will we get n plus 1 different lines? Like,
yeah, so you should think about this formula as describing n1 lines in direction 1 and 2 lines in direction 2 and 3 lines in direction 3. And I'm not sure if I understand what generalization are you proposing.
More, you said tn comma 0, so you should have more flavors, right? Like in a sense, like more.
No, so I see. So you're asking about the generators tn0, right?
Yes.
So, okay. So tn0 are different Hamiltonians of the integrable system. So the integrable system has infinitely many Hamiltonians. These are the Cauchy-Moser Hamiltonians, roughly. And the n just labels the.
So there are other Hamiltonians, the for high power in derivatives.
Yes.
Okay, yeah.
That's correct.
Then I understand.
So T10, T10 would be just sum of derivatives over these. T30 would be something that starts with sum of derivatives, sum of third derivatives multiplied by epsilon I to the second power and containing some extra corrections and so on.
Yeah, I understand. Yeah.
Good.
Yes. So when you say integrable
Yes.
system, so can you find the common spectrum of all these Hamiltonians? And
so we haven't tried. I expect you can for the doubled one. So let me tell you what the doubled one is. So the doubled one, you don't see the cursor, right? Can you see the cursor?
We see it perfectly. Yeah.
Okay. So so if you forget about these two terms and this term, so basically look at these 4 terms together with this term, you get a doubled Cauchy-Moser system that has been studied before, and people have identified the spectrum, if I remember correctly. And I can point you towards the literature, the papers. The tripled one I haven't seen anywhere. It doesn't mean that people haven't analyzed it. I just haven't seen it. And of course, I haven't seen studying its spectrum, and we haven't done it. We have just realized that these objects must exist, and we constructed them by using the holomorphic coproduct of the algebra A, and then we used it in some of our formulas, but we've never studied its spectrum. I would say it's open problem, I guess, and
Thank you.
So Mirek, you get in this way the rational Calgero models. So can you also get somehow by changing your geometry, the trigonometric or the elliptic models?
Yes, I think so. That's something that we haven't studied at all. I was planning to comment on this story at the end of the talk. I haven't done it.
Change the C to C star or to the elliptic curve, right?
Exactly. Yeah.
Okay.
So yeah, so I expected once if you change one of the C's by C star, everything should generalize to the trigonometric case. We haven't done it because we found that this system is the simplest one, and yeah, so we started with this one. But of course, there should exist a generalization of the full story.
Okay, thanks.
Okay, so let me now go back to the figure after defining the algebras A, N1, N2, N3. Let me go to the figure of composing two vertex operators. Let me take the following vertex operators. And indeed, one can sit down and check that they do satisfy the gauge invariance condition that intertwine the action of W algebra modes with the Kaul-Moser realization of the algebra Y of the algebra A 2, 0, 0. So these are again formulas that one can check. And analogously, we can fuse N1 lines with orientation along C epsilon 1 and 2 lines orientation along C epsilon 2, ending from the right to produce operator intertwining the action of TMN embedded inside Y001 with the action of algebra A, N1, N2, N3, A, N1, N2, 0, realized in terms of the differential operators above. Generally, we expect that this leads to a gauge-invariant endpoint of L, N1, N2, and 0, ending on S001. To identify the more complicated algebras Y, N1, N2, N3, one would need to consider more complicated, to employ the more complicated algebras Y, N1, N2, N3, one would need to consider more complicated surface operators such as S011, because the same issue that the line that we encountered before, that the line with the orientation along the third direction cannot end on the S001. But this should be totally doable. So with the elements above, we can study more complicated junctions by combining Miura operators and vertex operators fused along topological and homomorphic direction, and recover a Bradbridge story that I do not have time to discuss in its full glory, but I at least illustrated it on a couple of simple examples.
So if I'm not mistaken, your story about gauge invariance is just reading off from string theory, saying an operator is gauge invariant if it describes a consistent M2 brane. So for example, if you try to break an M2 brane on an M5 brane that it can't actually break on, you'd get something that's inconsistent, that doesn't preserve gauge invariance. That must be just that, right?
Well,
the string theory tells you exactly which are the gauge invariant ones, and everything else isn't, for the reasons that it doesn't describe a consistent M2 brane configuration.
Yeah, could be. But then would you be able to give an M theory derivation of the Miura operator, for example? I think that was one of the most surprising.
I think the way to derive these things is actually from the Q deformation of these theories, where you would start actually in type 2B string theory, where M2 has become D3 branes, and you understand everything about them, so you can just write down everything. I mean, it's a derivation in the sense that you have a weakly coupled system. M2 branes are mysterious. D3 branes are not mysterious because they just support gauge theories and three-dimensional gauge theory in a circle about which we know like everything. So yeah, you can derive all of this.
Yep. Well, good. That would be fun.
Sorry, I'm not sure. I'm not saying that I did it. I'm saying one can.
Sure. Yeah. Okay. We just realized there's this nice condition that satisfies by all of them. It somehow matches our expectations from the point of view of Kevin, and it leads to like this nice interplay between Coulomb branch algebras and W algebras. So that's my statement. And if there exists such a way to get, say, Miura operator and all those things somehow more naturally from M theory, that'd be great.
Yeah, I mean, basically, what you can derive from this perspective of D3 branes is, yeah, I mean, you can essentially, in essence, derive the corresponding operators in the in this UQ GL1 hat, and it's quantum toroidal algebra.
Yeah.
And by taking limits, you get all of this. It's a lovely story, yeah.
Yeah, I remember that you did something in that direction.
Yeah.
vertex operators.
If you want to use it, you're welcome.
But for that, you need C star instead of C, right? So the second equivariant parameter comes from there. Right?
No, you don't get extra. So the difference is that in the M theory picture, that's right. In the M theory picture, instead of two C planes, you have C star times C star. That's right.
Mm-hmm. Yep. Okay. So to illustrate that what I'm doing has actually many interesting and nice consequences, let me also briefly mention the connection to PT modules, because as a byproduct of our analysis, we define a class of modules with box counting associated to the Pandrei-Pandey-Thomas box counting of the topological vertex C lambda mu nu, labeled by a triple of partitions. So we've identified the gauge-invariant operator associated with configuration of n lines with orientation along epsilon C epsilon 1 and m lines with orientation along epsilon C epsilon 2, ending from the right. And we identified it with the following operator. The right action of A n M0 and the action of most of GL1 current algebra generates a rather complicated module for both algebras. There exists, one can easily project on an ANM0 module by taking an overlap with the highest weight state and obtaining the following expression. And one can check that action of AMN on this object, this product of differences of z's to some power, actually generates a nice highest weight module for the algebra AMN0, realized in terms of the Calogero-Moser-like description. And it generates a highest weight module with a basis labeled by Pandrei-Pandey-Thomas box configurations associated with the topological vertex CMN0. A trivial example of A100 acting on the identity produces the simple module, which is just generated by polynomials in single variable z, is an obvious action by z to the n and an obvious action of derivative, and with the character given by the following formula. This story actually turns out to have a generalization, and it turns out that one can generally define an A module labeled by triple of partitions lambda mu nu with the basis labeled by Pandrei-Pandey-Thomas configurations. The gauge invariance condition rating the action of W infinity and the algebra A then leads to a categorification of the relation between PT and DT topological vertices due to Pandrei-Pandey-Thomas. Unfortunately, I didn't have much time to discuss this story because it would take me another 2 hours or 1 hour at least. I just wanted to mention that this is a consequence of our discussion.
Can you explain a bit more? What do you mean by that?
Yep, I can say a little bit more. So, so the algebra W infinity, especially when written in terms of the affine Yangian of GL1, is known to admit a large class of modules labeled by triple of partitions. The basis of these modules is in correspondence with 3D partitions with that asymptote to the free partitions. This box counting recovers the topological vertex for DT invariants, the Donaldson-Thomas invariants. On the other hand, there's this, right, and on the other hand, there's this topological vertex from your paper, your famous paper, that is stripped off the McMahon prefactor as shown in the figure. So on the left-hand side of the figure, we have the Donaldson-Thomas Donaldson-Thomas topological vertex with the box counting due to Waffa, Reshitikin, or who are the
I think Pandripan and Thomas.
No. So Pandripan and Thomas give this box counting interpretation of the thing on the left. But before there were physicists, Waffa and others. The famous one, the famous paper where they give the box counting interpretation of the topological vertex times McMahon function.
That's Reshitikin with Waffa and Okunko.
Oh yeah, okay. Yes. So that's the paper I meant. Okay. So this is the box counting for the DT topological vertices on the left, and then there's PT topological vertices for the Pandrei-Pandey-Thomas invariants that are stripped of this McMahon function. And the thing that I'm saying here by categorification of by the claim of categorifying this relation between DT and PT topological vertices is that the left-hand side is a character for a module of W infinity algebra. And this is a module that comes from M2 branes ending on M5 branes when looked from the point of view of M5 branes. And the thing on the left that comes from the dividing by the McMahon factor is actually a character of a module for the Coulomb branch algebra associated to the M2 brane when we are looking at the same configuration, but not from the point of view of M5 branes, but from the point of view of M2 branes. And this can be then made very precise if I employ the Youngian basis of both of the algebras. And I didn't want to discuss it today, but is it somehow understandable what I'm trying to say? I'm just saying that there are two things. One is divided by McMahon function. You get one of them from dividing the other one by McMahon function, and one is a character of a module for W infinity, and the other one is a character of a module for the algebra A. And you can actually make this statement even sharper by saying that one of the modules comes from a co-kernel of some generator E0 of a fine Youngian of the other module.
If one tried to do this in more complicated geometries, which part would you be stripping off? Say easy one, C3 mod Zn, with the Zn action on on just 2 plane. C times C2 mod Zn.
Okay. Yeah. You're basically asking how many McMahon functions I should strip off, right? So yeah. I think the characters. I haven't investigated this question. My expectation is that what you're supposed to get is exactly the topological vertex partition function. So
the relation between DT and PT theory is, in some sense, I think, understood. In that, what people would say the relation is wall crossing. In that, you're counting BPS states, and in the PT theory, the BPS states of a D6 brane with D0 branes are absent because of the choice stability condition.
Yep.
Now,
so
you could be doing something else, which is describing a theory only on M2 branes, in which case there's part of the world that they simply cannot know about. For example, because they're essentially they wouldn't know about anything that comes from the bulk, which is somehow beyond them. They just know about their own local physics. So there are two different things that could be going on.
I see. Well, that's an amazing question, and I don't know an answer to. But so you're basically just asking if I'm doing the PT theory or something different, just by looking at the M2 brane.
I guess what's the interpretation of what you're doing? Certainly, categorification of a relation between DT and PT theory, that has already been categorified. So I mean, that on its own is well understood. So you may be doing something else.
Well, maybe. So I'm promoting this about statement about modules for some algebras. Has that been done?
No, that's new. That's the new part.
That's new.
That's new.
Okay. Good. Okay, so let me finally summarize. So today we have identified gauge-invariant condition satisfied by operator describing M2 and M5 brane junctions in twisted M theory, by giving the truncation maps for the Coulomb branch algebras, and by giving the coproduct from A to A times W infinity. We reinterpret basic objects from the M theory of BOA, such as Miura operator and degenerate fields, as building blocks gauge-invariant junctions. This leads to a new perspective on these objects and a connection between Coulomb branch algebras and integrable system, and the connection of W infinity of W algebras with Coulomb branch algebras and integrable systems. Composition of junctions seems to be consistent with fusion of lines along the holomorphic direction and surface operators along the topological direction, which allows us to build more complicated junctions, starting from the elementary ones. And I've sketched briefly that endpoints of M2 branes ending on M5 branes lead to W infinity modules labeled by triple of partitions when viewed from the point of view of M5 branes, and A modules labeled by triple of partitions when viewed from the point of view of M2 branes. The connection between them categorifies Pandey-Thomas conjectural relation between the DT and PT topological vertex. And just a short list of questions that are open and that are worth studying. So some of the claims we made are remain somewhat conjectural, and they deserve study. In particular, I expect the definition of PT modules that we gave, and I didn't have time to review today, should admit much simpler formulation, because the way I define it is pretty cumbersome. Natural question is generalization of our setup to configurations with M5 and M2 branes compactify on arbitrary free folds, something that Mina also mentioned. Our gauge invariance condition, together with other results, should be derivable directly from the perturbative analysis of 5-dimensional Chern-Simons theory along the lines of Kevin. Some of the modules we construct should admit a geometric construction also by correspondences acting on various moduli spaces associated to our geometry. And as already mentioned a couple of times during the talk, our story should admit a generalization by replacing C squared times R by C times C star times R, leading to a trigonometric version of Kaiser-Moser systems, or the configuration mentioned by Mina when we replace both of the C's by C stars. And finally, M5 branes can be supported on either of the two C's inside C2 times R. And that is a possibility that we have not investigated as well. So there's, I feel, a lot to be done and generalized. Thank you very much for listening.
Thanks, Miroslav. Let's see, do we have questions?
Yeah, maybe I can ask. So when you say that you can replace C by C star, you can do it independently in different directions. So you could have some model which is like half elliptic, like in one direction, and trigonometric in the other one, something like that. So you would even mix it.
Possibly. That seems to be an allowed configuration in M theory. So I would say there should be story behind it. I have no idea how to do it, but possibly if you start with the configuration that Mina suggests, taking the two C stars, one might be able to do some kind of classical limit of the corresponding setup and recover both of them.
And maybe I didn't understand one more thing. So when if you want to have elliptic model, you just replace C by C star or by really a torus, by an elliptic curve? Can you do that, like to make it compact? You know, like C
Yeah, I don't know. I haven't
moduli-
thought about it.
That's interesting because that's two different. I mean, it's essentially C star times C star is already elliptic, except that it has fixed complex structure.
Yeah, but it has complex dimension too, and yeah. So if you,
but in principle, you're right. You can also do C times an elliptic curve, which will, I think,
yes, because that
different.
is also flat. So maybe why wouldn't it work?
Yeah.
That's interesting. I'm actually not sure the two might be the same. So certainly C star times C star gives you the quantum toroidal algebra. If you did C times an elliptic curve, you get an additional parameter, which is the tau of the torus that you get to that enters, which is interesting. But algebraically, what happens, I don't know. However, I think the really interesting thing is that there you can derive everything in principle, just from perturbative string theory. Now, your Coulomb branches become Coulomb branches of 4D gauge series in a circle. And the nice thing is you see the manifest SL2Z symmetry.
Yes, that's one of the nicest things.
Let me know if you want to talk about this, because I somehow lost interest, but maybe I was wrong to lose interest. Your story is beautiful.
Yeah, sure.
Okay, do we have more questions? So in the end, what do you see a relation? Can you deduce the algebra A from the double infinity algebra in your story? My guess would be that the quantum toroidal algebra knows everything, and there's nothing more to know. But I don't know if that's true.
Did people study the toroidal version of A, or that's something like?
I don't know. I haven't seen it anywhere.
So when they talk about these shifted Youngians, are there also shifted quantum, you know, this double toroidal, or whatever the name? The
Do you know?
I mean, there's certainly this, there's a Coulomb branch algebra that arises, but this is just represent a particular representation of the quantum toroidal algebra. Yes, not a faithful representation, but you get it from there. So
but, But Mirek, the A is A representation of the W infinity? Is it that you put some generators to 0? It's not that you put some generators.
It's a subalgebra of the W infinity. You just need to, you forget about the A0 generator of the affine Youngian, and then you get A.
Okay. So it's inside.
Yeah, it's inside. But
but the arrow goes in the other direction.
Okay, so you cannot write a map from W infinity to your Coulomb modules.
Yes.
That's the wrong direction. Okay.
Exactly.
What do you mean by the arrow goes in the wrong direction? Sorry, I didn't understand.
So,
my representation theory isn't that good.
Yeah. So sorry. So if you want to represent you can go from A to Coulomb to the representations. No. If I give you generator of A, you know how to represent it in terms of derivatives and multiplication by Z, as Mirek wrote it. And now, if you wanted to do from W infinity, you would need arrow that goes through A. So from W infinity to A to Z and derivative with respect to Z. And Mirek is saying that the arrow is not going from W to A, but it is going from A to W. So you cannot kind of go backwards.
Yeah, I think that might be possible, but you have to introduce negative powers of Z. And we had some complication with that, with making the story work.
Yeah, that could be always, that's always this dream of doubling this W infinity. Yes. So you would get something bigger like they have in this toroidal algebra where they have SL2Z and so on. And here it seems to be broken.
So maybe one should really study the toroidal algebra.
Yeah, but the toroidal is very okay. Yeah, you lose some other things. You lose like this nice CFT locality, and you know, yeah.
I think the way to think about it is sort of derive everything you want to know in the Q world, and to get an intuition of how to think about it, you take you think about it from the CFT perspective.
Okay.
But the Q deform thing has always been more powerful. The only hard part was like exactly how to think about it, and the conformal limit tells you how to think about it.
Yeah, but even like I still do not understand, for example, the Q Virasoro, what it really is. You know, formally, algebraically, I can see what it is, but I don't know what it does with the 2D CFT. What it does with the
I know,
theory.
but it's an amazing thing. You see, the reason these Q double algebras exist and Q deformation of anything exists is the 2-0 conformal field theory has a canonical Q breaking of conformal symmetry, which corresponds to studying little string theory instead. Okay. And that fact is magical. It's a consequence of string theory. It's extremely deep. And it, to me, is the reason why these Q deform CFTs exist. And but indeed, how do you think about them? And essentially, it has all the structure of conformal field theory minus conformal invariance.
But also the locality, no, not only conformal invariance. I think the OPEs are somehow not. You don't have derivatives. You have some kind of long range.
You can't do everything.
Interaction. So it's kind of that is something that I miss. Yeah.
Yeah. I think there's no natural notion of fusion there. It's that, or at least the fusion to identity, I don't think quite works. I think.
Yes. You see, most of people got Q deformed in some way. Most of people do this, especially in math, for the reasons that you are saying. Yeah. But for example, for this SL2Z symmetry, I still don't understand if you really don't have it here, or you just need to double it, because in you know, the generators of the toroidal algebra are like labeled by Z2, by lattice with 2 integers, no? And here one of these integers is like mode number, which can run from -infinity to infinity, and the other one is spin. And you also don't want in CFT negative spins, and that's kind of the reason why you miss half of the generators and why you don't have SL2Z symmetry, because the SL2Z symmetry needs the other half of generators. It kind of needs these negative spins. And again, this is something that I'm not sure if you cannot add to it, even in the non-toroidal algebra. I mean, it's hard to get answers, you know, or someone telling you why really the toroidal is so different than this one, if it is really inherent property of this Youngian that it cannot have this added to it, or if it is really just that people didn't figure out how to do it. I don't know. It doesn't matter. This is just, you know, philosophical blah blah. Most of nice things you can transfer to Youngian, and then yeah, you get nice CFT and
yeah.
Yeah, whatever. These limits are also, some people say that the limits are very badly behaved when you send the Q parameter to 1. That, yeah.
No, there's a well-defined conformal limit, I think, which also is the string theory tells you how to take it. It should be fine, and it should tell you everything that, you know, exactly how to take it in the right way.
Yeah, but you have, for example, this rotation by 90 degrees. No, the what is it? S duality. Yes, of the SL2Z, and that one you could take the limit Q going to 1 before doing it, after doing it, and you should get some kind of incarnation of the CFT limit of the dual, of the S dual, basically like kind of S dual Youngian or something like that. And yeah, I don't know what this would be, and if it could be something really different than the Youngian. Yeah. And this type of limits are somehow problematic, I would say. At least this is what people say.
Well, there is one very special limit, which is taking the string scale of little string theory to 0 and infinity, depending on if you take the length, if you characteristic size of the string, you take it to 0. That's a very special limit, which should preserve all the structure, because you should land straight on the CFT on the same space.
Okay.
But of course, you can take other limits and they'll mean something else. Yeah. Possibly nothing. Okay.
Thanks.
All right, thanks everybody. Well, continuation of the seminar, we see you in January. And yeah, and send please lots of ideas for speakers. Great. Thanks, Miroslav. This was great. It was a lot of fun.
Thank you. Okay. Yeah. Have a good one.
Dobro, čau.
Dobro.